law of conservation of mass down here. Very simple. Law of conservation of mass. It'll be very short. And essentially, by experimentation, by chemists such as Lavoisier, who lived during kind of the Enlightenment, just before the French Revolution. He was a French chemist, Lavoisier, that in any chemical reaction, he did a lot more than just this, but this was sort of his like one of his major accomplishments. In any chemical reaction, the mass of products, so that's what's produced, is exactly equal to the mass of reactants. Law of conservation of mass. Sorry, I trailed off there. Law of conservation of mass. So in any chemical reaction, the mass of products is exactly equal to the mass of reactants. And what you infer from this is no matter is created or destroyed during a reaction. Let's take that even one level further, and let's just talk quickly about matter. Well, matter has mass and takes up space. So really, if you look around you, you're seeing matter everywhere you look. Even when you're seeing the gases in the air, you're seeing matter. Okay, so matter has mass and takes up space, and matter, at its very smallest bits, right? Matter is made up of atoms, right? Now, atoms are made up of smaller things, but for all intents and purposes, we can say that matter is made up of atoms. Since we're doing chemistry, and chemistry deals with atoms, the final statement that I want to make about this is that in reactions, atoms are not created or destroyed. Right? Not created or destroyed. They just change the compounds that they're in, or create compounds. We'll do a little example here, and then we'll be done. So imagine I have a balance, okay? Imagine I have a balance, like a balance beam. Yeah, kind of like a teeter-totter, exactly. Right? And we'll say that this thing is very, very precise, okay? And what we'll notice is that if we do a reaction such as this, and we'll get into reactions a little more tomorrow. Yes, please. So oxygen from the air plus magnesium metal will burn to make magnesium oxide, okay? Now let's look at the atoms that are involved, right? There's a magnesium. So let's say magnesium is this yellow guy here. And then there's oxygen, which looks like this, right? It's two O's together. And then they recombine over here to make magnesium oxide, right? Which is an ionic compound. Now, would this balance the way that I've drawn it? No, right? In fact, what are we missing over on this side? Well, we're missing one of these oxygens, right? There's two here, there's only one here. So this is going to get into a concept called balancing. We have to show that the same amount of atoms went in on this side come out on the other end, all right? So in this case, well, we need another oxygen over here, but oxygen can't really be on its own. It's always combined with magnesium. Now look, I'm short of magnesium over here, but if I do it like that, I now should have balance. The mass over here equals the mass over here. In order to do that, I had to put two magnesiums over here, and I had to make two magnesiums over here. This concept is called balancing an equation, and the reason we do it is because we want to show that no mass and no matter and no atoms are ever created or destroyed when we're doing chemistry. Okay? So we're going to look at this kind of concept going forward. Okay? And that is that. And